Today we'll talk about functions of random variables. So we have a random variable x, and then y is equal to g of x. In practical applications, we typically start with some random variable or a bunch of random variables, and we are interested in the distributions of functions of those random variables. So if let's say that x is discrete, and you have y is equal to g of x, and you are interested in the probability that big Y is equal to small y. So here you simply sum over the x probabilities. Specifically, you sum over the values of small x that are mapped by function g to small y. Okay, so let's see an example. So suppose that x is a non-negative integer, y is the floor of x over 2. So basically, if x is 0, floor 0 is 0. If x is 1, floor 1/2 is 0. Okay, and so basically 0 and 1 are mapped to 0. If x is 2, 2 over 2 is 1, and the floor of 1 is 1. If x is 3, 3 over 2 is 1/2, the floor is 1. And so 2 and 3 will be mapped to the value 1, and so on and so forth. Okay, so basically each two consecutive values of x will be mapped to a specific value of y, and we can write that the probability that big Y is equal to small y, this is the probability that big X is equal to 2y, plus the probability that big X is equal to 2y plus 1, because you get this value, y. Basically, if x is equal to 2y and you divide x by 2, you get y, and floor of y, which is an integer, is y itself. And if you add one, basically you get 2y plus 1 over 2 is y plus 1/2, and the floor will be also y. Okay, and so here again the story is that you take the values of x that are mapped to a specific small y, and then you sum those probabilities. Okay, what if x is continuous? Now, there are so many functions that you can define between x and y, and so let's talk about cases. What if the function g is a strictly increasing function? A function g, so basically this is y and this is x, and suppose that the function between y and x is strictly increasing, then the function is basically invertible. Okay, the inverse of the function exists, and the inverse itself is strictly increasing, as we know from calculus. Okay, and so now let's try to obtain the CDF of y. Okay, so again, when you do this transformation of random variables or apply a function to a random variable, now if you want to get the new distribution, you may start with the CDF of your new random variable, or you may go directly to the PDF, as we will see. But let's start basically with this method, in which we try first with the CDF. So what is the CDF of y? So this thing here is the CDF of y. Well, y itself is g of x. It's a function g applied to x, and in our case here, it's a strictly increasing function. So it's the probability that g of x is less than or equal to small y. So we have an inequality here. Okay, an event, and we are interested in the probability of such event. Now, if you have an inequality, and if you apply to that, to both sides of the inequality, a strictly increasing function, okay? For example, if you apply, if your stuff is positive on both sides, and you apply the logarithm, or both sides may be anything, but you basically apply the exponential function. Okay, in general, if you apply an increasing function to both sides of an inequality, the inequality is preserved. Nothing will change. So basically here what we will do is that we will apply the inverse function of g to both sides. Since it is strictly increasing, then actually these two events are equivalent. Okay, so these two guys are equivalent, and the probabilities will be equal. Okay, now if you apply the inverse of a function to a function, you basically get x. So g inverse of g of x, by definition, that's the definition of the inverse of the function, you get x. And on the other side, on the right-hand side, you get G inverse of small y, the inverse of the function applied to small y, okay? And so now we started with the CDF of y, but now we are able to write things in terms of the CDF of x, because this is the probability that x is less than or equal to something, which is the CDF of x. So this thing here is the CDF of x at, basically G inverse of y, okay? So if your function is strictly increasing and you want the CDF of y, what you can do is that if you have the CDF of x, f of f sub big X of small x, what you can do is that you can replace the small x, each small x in the function should be replaced by the inverse of the function g applied to y. So let's see an example. Okay, so x is non-negative. Okay, x is a non-negative random variable, and you take the square root of x. Okay, so y is equal to the square root of x. Now, so basically, if we block this function, so x is here. This is the domain of x. Okay, so this is x and this is y, and basically y is the square root of x. And as you can see, it is a strictly increasing function. Okay, and so what is the inverse function? It's the square. So here the square root, the inverse is to square, right? So x, so basically if you write x in terms of y rather than y in terms of x, you just square both sides, and no problem here again because everything is non-negative, so squaring will not destroy a sign or something like this. So y squared is equal to x. Okay, so what you do according to this line here, if you want the CDF of y, you simply take the CDF of x and you replace a small x by y squared. This is the inverse of the function. So the function is the square root and its inverse is to square. And so basically you go to the CDF of x and replace each x by y squared. Okay, if you are interested in the PDF of y, then we know that if the CDF is differentiable at a point, then basically you can obtain the PDF from the CDF via differentiation. Okay, so basically the PDF of y, now it's a small f here, you simply differentiate this guy with respect to y. So if you differentiate a CDF, it gives you a PDF, okay? However, of course, implicit in the argument is that the function is differentiable at the point in which you compute the function. So the derivative of the CDF is the PDF, but then you need to apply the chain rule because you are differentiating with respect to small y, and here the argument of the function is y squared. Okay, and so you need also to have, so here we have a chain rule. Okay, you need to differentiate whatever is inside, so the derivative of y squared is 2y. Okay, and so this will be, so given the PDF of x, this will be the PDF of y. Okay, and so again, if you do it in two steps, if your function that you are applying to x is a strictly increasing function, you take the CDF of x and then you replace a small x by the inverse of the function applied to y. And this, inverse of the function thing means just that you start with y written in terms of x, just express x in terms of y. Okay, and then you get the CDF of the new random variable big Y. Now, if you are interested in its PDF and the CDF is differentiable, then you can basically differentiate and you need to apply the chain rule. Okay. Now, in the particular case, if x is uniform from 0 to c, so here the PDF of x, so this is fx of x, x is between 0 and c, and so if the PDF is flat and is equal to 1 over c, so that the area under the curve is equal to 1. So basically, uniform 0c means that the PDF is 1 over c when x is from 0 to c, okay? And now what will be the PDF of y? If y is the square root of x, then again you go to the PDF of x, replace each small x by y squared, and then you need to multiply by 2y here, okay? And then you have the indicator function, okay? So basically f of x y squared, so this term that we have here, you go to the PDF of x, replace x. Where is x here? It's not outside because basically the function is piecewise constant, right? It is equal to 1 over c from 0 to c, and elsewhere it is equal to 0. So it's piecewise constant, and we just have 1 over c, but we have x here inside the indicator function. And so to get fx of y squared, you replace this small x by y squared, and so everything here is not negative. You can take the square root, and so basically this becomes 1 over c, the indicator 0, less than y, less than square root c. Now the full PDF of y will be again f of x with the small x replaced by y squared, which is the inverse function, and then don't forget the term that you get from the chain rule, and then you have this indicator y from 0 to square root c, which makes sense, right? So if y is equal to square root x, if x almost surely is between 0 and c, then y almost surely will be between 0 and the square root of c, okay? Another example, which is like sort of very useful in practice actually, which suppose that there is a random variable x whose CDF is strictly increasing. Okay, so it means that x is an absolutely continuous random variable. So CDF is basically, it's always increasing, no flat or constant parts. It's strictly increasing. Now, since again it's strictly increasing, there is an inverse, and let's apply this inverse to a random variable z, which is uniform 0, 1. Okay, so now our new random variable y is as follows. You have a random variable x with a strictly increasing CDF. You obtain the inverse, as we will see in an example, and then you apply the inverse to a uniform 0, 1 random variable. Okay, and the question now is, what is the distribution of y? Let's start CDF of y. CDF of y, by definition, the probability that big Y is less than or equal to small y. What is big Y? It is basically this function of z. It's the inverse of the CDF of x applied to the random variable z, which is uniform 0, 1. Now, the CDF is strictly increasing. Okay, and so again, if you do this in slow motion, you will take this inequality here, apply the CDF to both sides. Okay, because the CDF is a strictly increasing function, so this will not change anything. Okay, and then the CDF applied to the inverse CDF of z, that's z itself, by the definition of the inverse function. And then we have the probability that z, which is that uniform 0, 1 random variable, is less than or equal to fxy, which is the CDF of x evaluated at a small y. Now this is equal to fxy. Why? Because what is z? So z is uniform 0, 1. Okay, and so what is basically, so what is the PDF of z? The PDF of z is indicator 0, 1. Okay, so it is 1 between 0 and 1, 0 elsewhere. And what is the CDF of z? Basically, you integrate. Okay, so you integrate from 0 to z, 1 dz, okay, or d, whatever you want to call your dummy variable of integration, du, and this will be z. So for a uniform 0, 1 random variable, the CDF between 0 and 1 is equal to z. The probability that the uniform 0, 1 random variable is less than or equal to z is z. And again, graphically, this is obvious, right? Because if you have 0, 1, and this is 1 here, what is the probability that a uniform 0, 1 random variable is less than or equal to alpha? It's basically the area from 0 to alpha under the PDF curve. and so this is a rectangle, and the height is 1, the base length is alpha, and so it's alpha. So the probability, if we go back here, the probability that big Z is less than or equal to something is exactly equal to this thing, again, because Z is uniform 0, 1. So basically the CDF of Y evaluated at small y is the same as the CDF of big X evaluated at small y. So the CDF of Y is the same as the CDF of X. So why is this useful? You can use this trick to generate random variables belonging to a certain distribution if you are able to generate uniform 0, 1 random variables. Okay, so again, assuming that you are capable, you have some good algorithm for generating random variables from the uniform 0, 1 distribution, then using this trick here in the trick in the example, you can actually generate a general random variable. It's the constraint here is that we have basically a random variable that is an absolutely continuous random variable with a strictly increasing CDF. So let's see how, for example, you can use this trick to generate exponential random variables. So this is, basically we want to generate random variables. Our target distribution is the exponential lambda distribution, okay? And then what should we do? So the idea is, again, we apply the inverse CDF. We apply the inverse CDF. Okay, so Y. Let's write this here with a different color. So we have Y is equal to, we apply the inverse CDF to a uniform 0, 1. Okay, uniform 0, 1 random variable, which means that because the CDF is strictly increasing, it means that fx of Y is equal to Z if you apply f of x to both sides. So you can start with something like this. Okay, you say Z is equal to the target CDF. Okay, so this is the target CDF. And what is the CDF of the exponential random variable? If your random variable, okay, so if x is exponential lambda, then the PDF of x is lambda e to the minus lambda x, and then x is greater than, it's a non-negative random variable, okay, and the CDF is basically the integral of this guy, 0 to x du, and this will give you 1 minus e to the minus lambda x, which is here. Okay, so this is the CDF applied to R. So according to the rule, how do we generate the exponential random variable? Basically, what you do is that you express y in terms of this z, okay, which will be the inverse function. So z is 1 minus e to the minus lambda y. Then you start like playing with this equation to end with an expression which y is on one side and z on the other side, right? So you basically move this one to z, or basically move this z, z goes here as 1 minus z, exponential goes there, and then you take the logarithm of both sides, and this is what you get for y. And so if you generate uniform 0, 1 random variables and then apply this formula, log 1 minus z, and then you scale by minus 1 over lambda, what you will get is basically an exponential distribution with parameter lambda. Okay, note that in this course, when I say exponential lambda is basically used in the PDF as such, and the first moment of x is 1 over lambda. Okay, so again, this is a trick that it tells you that if you can build a good algorithm for generating random, uniform 0, 1, basically samples from a random variable, then you can use these samples to generate exponential, basically random variables, Gaussian random variables, and so on and so forth. Okay, let's now take a case in which the function g is not basically strictly increasing. In fact, it is saturating like this. So basically, g now is a linear function between minus c and c, where c is some positive constant, and then it gets fixed here. So c and minus c. So this is the relationship between y and x. Okay, this is the relationship between y and x. This is our, and as you can see, it is not strictly increasing. Okay, so again, if we want to write an expression, y is c if x is greater than or equal to c, y is fixed at minus c if x is less than or equal to minus c, and between minus c and c, y is x. So basically, this line here is a line with a slope of 1. And you can see that the possible values of y is only living between minus c and c, okay? And so y is between minus c and c almost surely, okay? Because whenever x exceeds c, y is c, and whenever x goes below minus c, basically y is equal to minus c. Now the question is, what is the CDF of y? Okay, so this thing here, again, it's the probability that big Y is less than or equal to small y. Now, what if a small y is chosen to be less than minus c? What is the probability that big Y is less than or equal to a number that is less than minus c? Well, this probability is 0. You know, because of the way that you basically construct function y. Function y, you know, basically it's living between minus c and c. It's never below minus c. Now, what is the probability that big Y is less than or equal to small y, and small y is equal to c or more? Okay, well, y is definitely there because y cannot exceed c. The probability that y is above c is 0, and so this is 1. Okay, so here again, it's from these things. I mean, they are not general. I mean, they are from how y is related to x. So in this problem, if a small y is less than minus c, the CDF of small y would be 0. If y is greater than or equal, the CDF of small y will be equal to 1. Now, if small y is between minus c and c, okay, then you are asking something like this. So given a small y, okay, so given a small y like this, okay, you ask yourself, what is the probability that big Y, the random variable y, is small y or less? And in our case here, what is the probability that big Y is from minus c to y? What is the probability that big Y is from minus c to y? So what are the values, you know, what are the values of x that are mapped to basically this range of y from minus c to small y, where y is living between minus c and c? Basically, all the x values below small y, right? Because remember that basically this straight line, over this straight line, we have y is equal to x. And so if the y coordinate of this point is a small y, then this is small y also, right? And so to get a big Y to be less than or equal to small y, then big X should be less than or equal to small y, okay? Which basically says that the CDF of y on this range will be the CDF of X evaluated at y. Again, it's not like a surprising thing. Y is equal to X over this range, okay? So the CDF of y, again, it will be the CDF of x evaluated at small y, okay? And so this will be the CDF of y. Let's take a particular example. So x is uniform from minus d to d. Okay, x is uniform from minus d to d, and so what is the? Let's plot the PDF of x. So here is minus d, here is d. And it's uniform, so basically this height must be 1 over 2d, so that the area under the PDF is equal to 1. And so basically what we have here is, this is the PDF of x. What is the CDF of x? The CDF can be obtained from the PDF. If you want the CDF of x at x, okay, so you ask yourself, what is the probability? What is the probability that big X is less than or equal to small x? So basically it's this area here, okay, under the curve. And so it is the height is 1 over 2d. The width of the base is x minus d, okay? And this is true for x between minus d and d, okay? So this is if x is less than or equal to d. Okay, so this is the CDF. So basically below minus, if x is less than minus d, basically the probability is 0 because x is between minus d and d almost surely. And if x is greater than or equal to d, this is 1. And between minus d and d, you do it via integration, okay, and you will basically get this result. It's 1 over 2d x plus d. So that's the CDF of x, okay, which is plotted here. So it's, you know, that the PDF is constant, the CDF is a linear function, and it's 0 at minus d, it's 1 at d, and it goes linearly between these two guys, okay? Let's assume for the purpose of this example that the c used in the g function, so this is the c, the parameter of function g. So let's assume that c is strictly less than d, okay? And so minus c and c is like this, okay? So again, the function is parameterized by the parameter c. Between minus c and c, y is equal to x. If x is above c, y is c. If x is below minus c, y is minus c, okay? And so now we have x itself, that's the distribution of x, and the distribution of x is uniform from minus d to d. And again, let's assume that d is greater than c. D is the parameter of the PDF of x. C is the parameter characterizing the function that basically generates y from x. Okay. Now we have a general formula. We have a general formula for the CDF of y. Okay, and so now what to do is basically to plug in. Okay, so now we have a specific value for the CDF of x. The CDF of x is given by this expression. Okay, now you ask yourself, what is the probability that y is less than minus c? This is 0. Okay, again, look at the function. The function tells you that y never goes below minus c. Now, if you ask what is the probability that y, big Y, is less than or equal to small y, and small y is basically greater than or equal to c, that's 1. You know, y cannot exceed c, so basically the probability that y is less than or equal to some small y that is greater than or equal to c is 1. And in between, you have the CDF of x, and basically in between, the relevant part of the CDF of x is this linear part here between minus c and c. So it's that line, and so you simply take the formula for the CDF and you replace a small x by small y. Okay, so this is basically f of x, the PDF of x. With small x evaluate small y, but of course this should be which one of those three guys. It's basically for x between minus c and c. Okay. So if you want to plot this CDF of y, basically below minus c it's 0. And then between minus c and c, it is this function here. If you put y, so what is f of y of minus c? So basically, it is 1 over 2d minus c plus d. Okay, so it is 1 over 2d, d minus c. So there is a jump. Okay, there is a jump here, a possible jump. And then basically at c, the CDF is 1. But if you go a little bit below c, you put y here equal to c, you get this value here. So you possibly get 2 jumps at minus c and c. Are these like surprising or anything? No. Because of the structure of your function, because your function basically have these two flat parts, actually there is in general a non-zero probability that y is exactly equal to minus c. So what is this probability? That y is exactly equal to minus c. Y is equal to minus c. This is exactly equal to the probability that x is less than or equal to minus c. Okay, and so it is the CDF of x evaluated at minus c, and this will be d minus c over 2d. Okay, so is there a non-zero probability that y is equal to c? Again, the fact that the random variable takes, a specific, one value, a single value with a positive probability, it means that you have a jump in the CDF and vice versa. If you see a jump, you know that basically random variable big Y, it takes, its probability of being exactly equal to C is something that is strictly positive. And what is it exactly? So what is the probability that Y is equal to C? What are the values of X that are mapped to C? So this is the probability X is greater than or equal to C. X is a uniform random variable, so we don't really care about, being greater than or equal to. And so this is 1 minus the probability that X is less than or equal to C. So this is 1 minus the CDF of X evaluated at C. So this will be the jump here that you have between at C. And it gives you the probability that that y is exactly equal to c. So you can see from the CDF that you start with x which is an absolutely continuous random variable. Y is a mixed random variable, so y is mixed. Okay, because it has a continuous part and a discrete part. You start getting jumps in the CDF of y because actually your function, the function relating y to x, is flat. It's flat from minus infinity to minus c, and from c to infinity. Okay, so another function, a bit more complicated function between x and y. So some people call this is the soft thresholding function. So here again, this is y, and this is x. And now between minus c and c, if the value of x is between minus c and c, y is 0. And then if x exceeds c, the relationship between x and y will be linear with the slope 1. And if x is below minus c, the relationship will be linear with the slope 1. And so this is the expression, okay, between y and x. Okay, so this is your function relating x to y. Again, the question in this chapter is, if you know the distribution of x, let's say the CDF of x, can you say something about the CDF of y? Can you obtain actually the CDF of y? So how can we do so for this particular g function, which basically looks like this? Okay. Now, suppose y is less than, small y is less than 0, and you ask yourself, so you are interested in the CDF of y when small y is less than 0. So this thing here I'm studying is fy of small y, and y is negative. Okay. So you are asking, what is the probability that small y is less than, is that the big Y is less than small y, which is chosen here to be negative. Okay. So here we are asking, what is the probability that big Y is less than or equal to small y, and small y is negative. Okay, so we are asking about big Y being from minus infinity up to this. Okay, so this is the region we are in. This is basically big Y being less than or equal to small y. So what does this correspond to in terms of the random variable x? So if big Y is less than or equal to small y, then big X is less than or equal to what? Okay, so what is the equation of this line here? So this line here, according to the function definition, this line here is x plus c. So this line, y equals x plus small c. So if big Y is equal to small y, what will be the value of x? It will be small y minus c. Small y minus c. So this will be this point here. And now, big Y less than or equal to small y, and y is negative, small y is negative, is equivalent to basically big X less than or equal to small y minus c, from minus infinity up to this point. And so basically the solution will be the CDF, in terms of probabilities, the probability that big Y is less than or equal to a negative small y will be the CDF of X evaluated at y minus c, which is written here as minus c plus y, okay, y minus c. Okay. Now, what if small y is positive? So again, you are interested, you are asking, what is the probability that basically big Y is less than or equal to small y, but that now that it's positive, okay? So you are interested in big Y being from, minus infinity up to this point, which is a small y. Again, what is the corresponding range for random variable x? Well, what is the equation of this straight line? Y is equal to x minus c. So basically this is y equals x minus c, and so small y is equal to x minus c, so big X is y plus c. So big Y being small than small y here is for a y that is positive is equivalent to basically x, big X being smaller than c plus y, and so basically the CDF of y here will be the CDF of x evaluated at y plus c. CDF of x evaluated at y plus c. Okay. Now, do you need to worry about y exactly equal to 0 and so on? So let's not forget something, that any valid CDF is a right continuous function, right? So this is why you can actually study y equals 0 specifically, but again, this can be useful actually, that you say, okay, this is fyy. Okay, so if y is negative, okay, so we have this view. If big Y is less than or equal to a negative small y, then it must be the case that big X is less than or equal to small y minus c. Okay, and so here we have f of x small y minus c, and if y is greater than 0, you'll find this is f of x y plus c, like this. Now the CDF function is right continuous. What does this mean? It means that, so at 0, at y equals 0, okay, so this is the formula for the function for strictly positive y. This is for strictly negative y. Because remember, what is the right continuous function? If there is a jump in the function, the jump is like this, right? It's always the case, so you won't so should we have a third line? Or should we have an equality here or here? What do you think? So we have three options. So do we really need to investigate small y exactly equal to 0?
No.
No, right? It's here, right? It's with this one. Okay, you can verify. Okay, so you can you can basically do that. You ask yourself, what is the probability that big Y is less than or equal to 0? Basically, big Y less than or equal to 0, which means that big Y is on this green part here. Now, what are the values of x that will give you a y that is less than or equal to 0? Everything from minus infinity to c. everything from minus infinity to c. So basically f of y 0 is basically f of x c. Okay, we have equivalence between these two guys. Y less than or equal to 0 is equivalent to it. It's if and only if big X is less than or equal to C. And now you get this if you just take this formula and put Y equals 0. And again, like if you want to be time efficient, you can exploit right continuity regarding the border cases, you know, the boundary cases. And it will always look like this. And if you see the notes, I'm trying to write everything basically to exploit this right continuity property of the CDF. So you'll find that I'm always, if I'm writing a range for small y, it's strictly less than something, but strictly greater than or equal to something. Okay, you know. It may be useful. Again, it may be useful, and you can actually do things two ways. You can basically study this case alone and then make sure that actually the resulting CDF is right continuous. Okay, so I mean, it may give you like a way to check things or to do things, you know, basically efficiently by simply focus on y greater than 0, y less than 0, and say y being equal to 0 should be part of this part, you know, of this branch of definition here. Okay. Now, let's suppose that x is like in the previous example. It is uniform from minus d to d, and then so this is the CDF of x. Remember, this is the CDF of x. And now, so this is a bit more tricky than the previous function g. Now, look at the general CDF of y is like, if y is less than 0, this is the result. If y is greater than or equal to 0, this is the result. Okay, so let's try to apply this. So f of y equals, and then y less than 0. Y less than 0. So if y is less than 0, if y is less than 0, you will put it here, right? So y is something negative, and with a minus c, so it's minus c minus something, okay? So what is the CDF of x? What is the CDF of x? Well, the CDF of x here is a bit tricky because in this case, again, we are talking about the CDF of x below minus c. And actually, this is composed of two parts. A linear part with a non-zero slope, and a flat part like this. Again, now you want, like, again, so you obtain the general solution. Now you want it to be like specific. What if x is uniform from minus d to d? Then, you know, it may be tempting that you say, okay, I will just copy these two guys, replacing f of x by its expression. But f of x itself is defined in pieces. It is not just the same. If it's a single formula, you will just plug, you know, replace small x by minus c plus y, you put it here, c plus y, you put it there, you are done. But the problem is that it is basically a flat part equal to 0 to minus d, then a linear part with the slope 1 over 2d, and then it is flat at 1 again. So if you investigate y is less than 0, which means that you are talking about minus c and then a negative number, then you are talking about this part, the part below minus c. But then there are two cases actually. A case in which the CDF of x is 0, and then the case in which it's this linear part. So when is the CDF of x equals 0, right? So what we have is that f of x minus c plus y, if minus c plus y is less than minus d, then f of x of minus c plus y is 0, right? Because again, if y is negative enough such that minus c plus y is less than minus d, then you are hitting this part of the curve. But if minus c plus y, okay, let's put it like this, if minus c plus y is greater than or equal to minus d, and still we have y is less than 0, then fx minus c plus y is the linear part. So, in other words, if you write f of y for this particular example, you will need to take this first line and split it in two parts. Okay, so you will have basically the first part will be y less than minus c minus d, y less than minus c minus y less than minus c plus d. If this minus c goes to the other side, minus, so it's minus plus c minus d. Okay, in this case, the CDF is 0. Then, if y is less than 0, but then greater than or equal to this threshold value, c minus d, then we are talking about the CDF of x. We are actually talking about the CDF of x in both cases, but now in the second line, we are talking about this linear part. Okay, and so we just copy 1 over 2d. Okay, and now we can replace this small x by minus c plus y plus d. And so a line here becomes two lines here, because again, y less than 0 should be divided into two ranges to account for the fact that the CDF of x itself is defined in a piecewise fashion. It is 0 below something linear line, it's a linear part with a slope 1 over 2d from minus d to d, and then above d it is flat at 1. And the same story below. So basically this second line here will be divided into basically two things, because if you are above 0, okay, if you're above 0, now again, you have two parts. You have the linear part, and then you have this flat part here. Okay, so you will end up with a function with four, pieces. Again, so this is like sort of the difference between this problem and the previous one, is that you need to be like, if you have a function evaluated at something, be careful if this function is defined in a piecewise fashion. Okay, so that's the moral of the story. So if f of x is some, function that, it has a formula that is valid for every real number, basically you will end up just taking this function and putting small x minus c plus y and c plus y. But if it's piecewise defined like such, you need to be careful. Okay, you need to be careful, and this will be the CDF. Again, it's the same story, that you will get a jump. And what is this jump? The jump at 0 means that there is a probability that y is exactly equal to 0. So x is an absolutely continuous random variable, but y can be equal to 0. How is this the case? Yeah, from here. You can see it directly from here. That what is the probability that y is exactly 0? It's the probability that x lives between minus c and c, right? If x is between minus c and c, then y is 0. And if x is uniform from minus d to d, the probability that it is between minus c and c will be what? Okay, so this is the PDF of x, 1 over 2d, and it is from minus d to d. And if we ask ourselves what is the probability that it is from minus c to c? From minus c to c, then it's basically this area. So this area, it will be 2c over 2d, which is c over d, and this will give you the value of the jump at 0. Again, our resulting random variable is mixed, and basically this is its CDF. Okay. There are more of these functions in the notes. Okay, so again, make sure that you go through actually all, after the second exam, make sure that you go through all the examples. They are useful, and again, those functions they are not fictitious. They appear actually. There are so many applications that make use of those functions. Okay, and so if you suppose that your input x to one of those functions is random with a certain distribution, you will be interested in obtaining the distribution of the output. Okay, and so more examples in the notes, and now let's go to the method in which like you obtain the PDF direct. So in the previous case, it's like I get the CDF, and if needed, you can obtain the PDF from the CDF via differentiation whenever the CDF is differentiable, and so on and so forth. But there is a method for like obtaining the PDF directly. It's a very lovely method, and basically it is given by this expression here. You need the function g to be differentiable. Okay, so the function does not need to be strictly increasing or anything. It needs to be differentiable, and we need the first derivatives basically of the function to be continuous. And this is needed in the proof. The proof is in the notes, and the idea that if g is differentiable and its first derivative is continuous, then basically there will be points on the function around which the function is locally invertible. Okay. You don't need to know the proof. You can read it. It is in the notes. Here we will just make use of the final result. Okay, so you have a function that is differentiable and it has a continuous first derivative. You want the PDF. Okay, so this is the PDF of y evaluated at small y. What do? Then you take the function g of x equal to small y, and you solve this. Solve g of x equal to small y. Okay? And you get the solutions. Okay, you may get no solution, you may get one solution, two solutions, and so on. So suppose that g of x1 is equal to y, g of x2 is equal to y, and so on. Okay, and of course, you know, this is best seen via an example, and an example is coming. Okay, so don't worry. But you know, you solve g of x equal to y, and you get basically those values of x. So basically, the PDF, the required PDF, is a sum involving those solutions to the equation g of x equal to small y. What are the terms of the sum? Numerator, denominator. Numerator is basically the PDF of x. So the numerator is PDF of x at xj. Okay, so that's the numerator. What about the denominator? So denominator is the absolute value. Okay, so this is absolute value. You cannot put something negative here. The absolute value of the first derivative of g, the absolute value of the first derivative of g evaluated at xj, and hence it makes sense that we require that basically this first derivative is not 0, so that we do not divide by 0. Okay, so this is the expression, and it can automatically gives you the PDF. The PDF automatically gives you the PDF of y. Okay, so let's take an example. So this is the relationship between y and x. Okay, so y and x are basically they have this relationship. It's a function y is equal to x squared if x is between -1 and 0, and y is x cubed if x is between 0 and 2. Okay, so this is the relationship between y and x. It's again piecewise defined. So basically, for x between -1 and 0, it is like sort of a quadratic curve like this. So here over this y is equal to x squared. But when x is between 0 and 2, we have a cubic curve. Okay, so basically here we have y equal to x cubed. That's a function. Okay, and its first derivative, okay, is 2x. 2x over the negative range, 3x squared over the positive range. Now you ask yourself, what is the PDF of y? Okay, so of course, I mean, you will not solve for every single value of y. You need to think about like ranges of values that can be solved like in one shot. Okay, so let's suppose that your small y, okay, so you have basically this curve here, and this is the point, so this is the point -1 and 1. So basically each y that is below 1, it has two corresponding values of x, but above 1, basically there is a single value of x giving you the corresponding y. So the trick here is to say, okay, let's investigate this, that y is from 1 to 8. So y is somewhere 1 to 8, 1 to 8, because the function is defined up to x equals 2, and this point is 2 and 8. So you first say, okay, I will investigate a y that is between 1 and 8. Now, for any y of those values, what is the corresponding value of x? We get it from, so you plot a horizontal line, y, it hits the function between x and y in just one point, which is this one. And what will be the value of x giving you the required value of y? X will be equal to the cubic root of y, small y. Okay, so you will take y from 1 to 8. In that case, if you ask yourself, so in this range, on this interval, g of x equal y has one solution. Okay, specifically, that x is the cubic root of y. This is not, something that is magical. You get it just from the definition of the function. Okay, and then what you do is that you plug in. Okay, so in our case here, when y is in this range, the summation is just one term, and so you need to go to the PDF. You need to go to the PDF of x, and basically evaluate this PDF at xj, which here will be the cubic root of y. Well, it's flat over this range of x, which corresponds to the range of y from 1 to 8. The PDF is flat and is equal to 1 over 3. And then, so that's the numerator, as I said above. What about the denominator? So in the denominator, basically, you have the function, okay, the function. So you need the derivative of the function. So basically, g1 of x is equal to 3x squared. Okay, and then you write it down in terms of a small y. Okay, so you express things in terms of a small y. So you write it, so express in terms of small y. So y is equal to x cubed. So x is y to the power 1/3. And so the first derivative will be equal to 3y to the 2/3. Okay, and this is what we have here. And this thing is positive, and so we do not need to put the absolute value. It should be there. If you get a negative thing, it should be positive. And so basically the PDF of y on this range will be 1 over 9, basically, and also in the denominator we have y to the power 2 over 3. Now things get more interesting when y is between 0 and 1. Okay, so let's talk now about this case, y between 0 and 1. So remember, this is y and this is x. Now between 0 and 1, okay, so we have this is the quadratic part, this is the cubic part. Okay, and so this will be 1, 1, and here this function is y equal x cubed. This is -1, 1, but this part y is equal to x squared. And now we are talking about a y that is basically here, like, okay, so this is a small y, and now we have two solutions. If you ask yourself, what is g of x equals y, now has two solutions. What are these two solutions? So there is a positive solution and a negative solution.
One and negative one.
No, I'm not talking about small y exactly equal to 1. I'm talking about small y in this range. So generally, what will be the solutions?
Square root of y and the third root as well.
Third root of y, that's correct from this side, but the other side, the x is negative, right? So cubic root of y and minus square root of y. Okay? So cubic root of y, we get it from this branch here. Again, the function is defined as such. And from the other side, you have y equal to x squared. And as you can see from the graph, that basically the x giving you this particular value of y will be a negative x. So our solutions are basically cubic root of y and minus the square root of y. And what you do is that now you have two terms. So if you go to the general formula, now we actually have two terms and not just one term. We have two terms, and again the PDF here, because of because the random variable x is uniform, then basically the PDF just give you these constants 1/3, 1/3. But in the denominator, you need to find the derivative of the function, basically evaluated at the solution, and you must use an absolute value. Okay, so for example, that if g of x is equal to x squared, then the first derivative is equal to 2x. So the first derivative evaluated at minus square root y will be minus 2 square root y, but we need to take the absolute value of this thing, and so it should be 2 square root of y. Okay, so what you find in the solution will be the absolute value. Very important, because you may it's a typical mistake, like just to forget this absolute value. You must have this absolute value. Okay, so now we have two terms, and then you can combine them or write them whatever way you like, and this is the PDF of y. So you can obtain it directly using basically this function here, this expression here, and this expression again is very nice. And typically, you are required, it's better like to plot the relationship between y and x, and actually to get to the number of solutions sort of graphically, to have a sense of whether like you have just one solution or two solutions, or maybe there is a range, right? So here, like in this particular example, then if y is greater than 1, we have one solution. If y is between 0 and 1, we have two solutions. And in the notes, you'll find another example that is very important also to basically study. Okay, then for later uses, we want to learn the Leibniz rule for differentiation under the integral sign. So what if you have a function like this, f of x comma t, and you integrate this function with respect to x from a lower bound that depends on t and upper bound that also depends on t, and our interest is basically the derivative of this function with respect to t. Okay, so we have t. T is in the function, is in the integrand, the function that you are integrating. T is in the lower limit of integration. T is in the upper limit of integration. Okay, and we are interested in basically differentiating this thing here. Now, of course, there will be conditions for the for this result to exist and to have a certain form that I will talk about. But for the purpose of AMCS 143, if you find yourself basically in a situation and you think that this result is needed, just use it. Okay, you do not need to justify it or even to basically think about under what conditions it will be valid. Okay, so what is the result? Again, there are conditions, but don't worry about them. This differentiation here has 3 terms. Okay, so you have basically 3 terms. What are the 3 terms? Okay, so term number 1, the first term, is basically an integral that looks exactly like the original integral, same lower limit, same upper limit, but in the integral you integrate the partial derivative of the function with respect to t. So partial f with respect to t. So this is the first term. The second term is, and the third terms are not integrals. So this is not an integral. So you basically take the function you are integrating. So this is the integrand with the dummy variable of integration replaced by the upper limit. By the upper limit. So you take fx of t and you replace x by beta of t. And you need to multiply by the partial derivative of beta with respect to t. Like this. Okay. And then the third term that we have is, again, it's not an integrand, it is basically the integrand with the dummy variable of integration replaced by the lower limit, which is alpha of t, and then you need to multiply by the partial derivative of alpha with respect to t, and then there is a minus sign. Okay, there is a minus sign here. Okay, so here with a plus sign, here with a minus sign. So those are our basically terms, three terms. Okay, now what if the lower limit or upper limit of integration is like infinity? No problem. I mean, just treat infinity as a constant. Okay, again, you know, we will not like enter into, you know, especially when basically the limits are infinity, the conditions for validity are more strict and, you know, are tedious actually to check. So, you know, just apply this rule, treating plus in, if alpha of t is minus infinity or beta of t plus infinity, just to treat it as if basically we have a constant. Okay. What is the question?
Professor, why are we multiplying by the partial derivative? Shouldn't we just take the partial derivative of that expression? Like,
no, I mean it's a formula with a proof. I mean, why shouldn't?
Okay. Okay.
Yes. So basically, this thing here, I mean, it's basically this is the result. If you want to differentiate this thing, okay, then you get these three terms, and again, we not take the proof or even like the conditions necessary for the proof to work. Best seen by basically doing an example. Okay, so let's take this first example here. Okay, so what is the derivative dt? You know, we want to differentiate this one. Okay, so
Here the f of x is not in terms of t as well, right?
Yeah. So but okay. So basically, first term is 0 because integrand doesn't depend on t, and this is great because the first term is annoying. It's still an integral that involves basically the partial derivative of f with respect to t. If there is no t inside the integral, you just say goodbye, and then basically this is 0. Okay, plus second term 0. Well, upper limit of integration is, in our case, is a constant. So if it is infinity or 7 or 17 or anything, you will need to take the partial derivative of beta with respect to t. If it's a constant, well, that's 0. Then a minus sign. Don't forget that there is a minus sign. Third term. So third term, you need now the partial derivative of t with respect to t. So dt by dt. Okay, so that's 1. Okay. And then you need to take the integrand and replace the dummy variable of integration by the lower limit of integration, which is minus t squared over 2. Right? So what is the result of this differentiation? It will be minus e to the minus t squared over 2. Okay, so yes, sometimes you know you can see that 2 of the 3 terms will be 0. You can check this second example. You'll find that one term is 0 and the other. So for example here, the third term will be 0, right? Because the lower limit is 0. So basically, when you differentiate alpha with respect to t, alpha is constant, and so the derivative is 0, and so on. Okay, so you don't like sometimes, yeah, it's very very typical that you find that one or two terms are equal to 0. Not a problem. Okay, so this is again the rule, and we will apply it extensively. Let's use it. Now we have a function of two random variables, and it's a very important function, okay, which is basically x plus y. Okay, so what is the distribution of x? What is the distribution of x plus y? I gave you two random variables. So previously it's like x, and you apply a function g of x. G of x is equal to y, and then you are interested in the distribution of y. Now we have two x and y. So what is the PDF, CDF, and PDF of x plus y given their joint distribution? An extremely important problem in probability and statistics. In fact, like in many basically applications, we have not just the sum of two random variables. We have basically a sum of actually sequences of random variables that actually may be infinite. And so this is like the beginning of the story. So again, sums of random variables are very, very important. Okay. So let's go first for the CDF. The CDF of z. So this is the probability that the sum is less than or equal to small z, and the sum is equal to x plus y. So what is the probability that x plus y is less than or equal to small z? Okay, so as you have studied for the coming exam, basically how can you solve a problem like this? You just have two random variables, x and y. So you can just do this x and y, and you see where is the region on which I need to integrate. So here the region is that you need x plus y to be less than or equal to z. So you draw the line. What is the line x plus y equal to z? It's a line that has basically slope of -1 that looks like this, right? So if x plus y is equal to small z, then when x is 0, big Y is z. Okay, so there is a point here 0 z. And if y is 0, then basically x is equal to small z. So it's a line of slope -1, and it looks like this for a general z. And we are interested in the event that x plus y, so basically this is the line x plus y equal to z, then we are interested in x plus y less than or equal to z. Okay, and so here I am sort of assuming that that is positive, so without loss of generality, z is positive here. And the region in which x plus y is less than or equal to z will be this region. Okay, so to obtain the probability that x plus y is less than or equal to small z, you need to integrate the joint PDF of x and y basically over this region here. Now we are integrating a PDF, and so it is a non-negative function. By Tonelli, we can do the integration in any order of our choice. So let's fix an x and then integrate first with respect to y. Okay, so if we fix an x, so let's take an x here. So this is a small value of x. And so for this value of x, so x, of course, generally can go from -infinity to infinity. So x -infinity to infinity. Now for this particular value of x, what should be the range of integration for y? Well, y goes from the bottom here from -infinity up to this point here. And what is this point? This point is a point on the line. So if big X is equal to small x, big Y will be equal to z minus small x. Okay, so this will be from -infinity. Okay, so you start here from -infinity, and then you stop at this point. Okay, and so Y will be from -infinity to z minus x. Okay. So general, and actually this idea is general. Like if I give you two random variables and a certain, inequality or something like this, the first order of business. I mean, if you want like to visualize what is happening, draw the xy plane and then see basically the region on which you are integrating, and then basically, write properly your limits of integration, and then you do the integration. This will give you the CDF of Z. Okay. Now we are interested in the P, because X is generally from minus infinity to infinity, right? I mean, generally is from, it goes from X. It can be any value from minus infinity to infinity. There is no restriction on X. Okay. But once you fix X, basically Y will be from minus infinity to X. Or alternatively, you can write down this integral as such. You can take dy from minus infinity to infinity. Now, if you fix a Y like this, X will go from minus infinity, and then you will stop here at Z minus 1. What? Say again.
Yeah, I was just saying Z minus Y.
Yeah, okay, yeah, great. Yeah. Okay, so yeah, so again, there is a variable that the outer variable, like it takes its range. The outer variable, it takes its range. You just need to think about it. Yeah, it's basically sometimes like you just have to like do things without actually drawing them. Okay. So here again, the idea is that it is better to it's a good question, by the way, because like in practice, actually, you will sometimes have to basically do things in many, using many random variables. And sometimes like you need like to have the rule, like to say the rule rather than basically telling it. So in our case here, like I can say this, so I have X and Y. I can again take one of those random variables, take it from minus infinity to infinity. Our event is X plus Y. X plus Y is less than or equal to small z. Fixing X at small x, we have big Y less than or equal to Z minus small x. So we integrate big Y from minus infinity to small z minus x. Okay, so here is a story without any drawing, using the event itself, the definition of the event itself. So you can do this. Okay, you can say, well, I mean, I will not draw anything. I'll say, okay, X is a general random variable. Let's say that, we'll basically integrate first with respect to Y, fixing X. So X, we can fix it at anything. In general, it goes from minus infinity to infinity. Then Y basically, if X is fixed and we are interested in the event that big X plus big Y is less than or equal to small z, then big Y is less than or equal to small z minus small x, using just the inequality in the event that we are interested in. Okay, it's doable, and sometimes actually this is what you will have to do. Now this is the CDF of Z, okay, and it's a double integral involving the joint PDF of X and Y. Now what is the PDF? What is the PDF of Z? Okay, what is the PDF of Z? So how do we obtain the PDF from the CDF? Differentiation. Okay, and so we need to differentiate this guy here with respect to Z. Okay. Now this may seem like we will apply. I mean, if you want to do things in slow motion, it's a differentiation that we can do in 2 steps. Okay, so we have integral from minus infinity to infinity. And then we have a function of Z, okay, a function of Z here, and then we have basically dx, okay, and this function of Z is minus infinity to Z minus x, and f of x y dy, okay. So we apply Leibniz. So you differentiate this with respect to z. Okay, so what will be the first term? First term will be integral, and then we differentiate basically the inner one. Okay, so what is the second term? 0, exactly. Third term 0, 0, upper and lower limits are constants or are treated as constants. Okay, so basically, you can apply Leibniz and again take the integral to the inside. Take the integral to the inside. Now, this guy, Leibniz again. Again, because basically we have now integral from minus infinity to infinity, z, and then we have this integral from minus infinity to z minus x, f of xy, x comma y, dx, dy, dx. Okay? So we have this, now we are applying this basically to here. Now, if I apply Leibniz again, now, is this thing function of z? Is the integrand the function of z? No, it's the joint PDF of x and y. So first term 0, integrand doesn't depend on z. Okay. Second term, it will be the derivative of z minus x with respect to z, and then you take the integrand and you replace the dummy variable of integration, which is y, with z minus x. So z minus x. And what about the third term? Third term, 0, because lower limit is minus infinity. Okay, so what the survivor is just basically, here is our hero here. It's basically this one. This is the second term. And so, again, if you apply Leibniz in slow motion, okay, maybe when I wrote it here, and in the notes you'll find that I did it like, in one step, in one line. But actually, I mean, if you want to do things in slow motion, because we have a double integral, it's like you do it twice. So you can basically imagine that the second integral is just a function. Apply Leibniz, and by its application, you will have to differentiate whatever is inside the function, and then apply Leibniz again. And you end up with basically this term here, and the derivative of z minus x with respect to z minus x is a linear function in z, treating x as a constant. So basically the derivative here is equal to 1, and we get this result here. Very important result. It's a very fundamental result in probability and statistics. Tonelli basically, Tonelli basically it's to tell you, it's to tell you that you can interchange the order of the double integral. So in our case here, it means that you can basically do the integration on any order of your choice. You can do the integration any order of your choice. But then we need now to do something else, which is to differentiate with respect to parameter, that this parameter like exists in a limit of integration or something like that. Okay, and in that case, our function, because actually we are integrating a PDF, which is like sort of a nice function, it's L1 function and so on. So it, take it for granted, it will be applicable, and you apply Leibniz. Okay, you don't need to think about it. But Tonelli will tell you that you can redo this problem actually integrating first with respect to x and then with respect to y, and in this case you will get this result here. So it's an equivalent result. The joint PDF can be written like this or like that. Both are equivalent and both are basically justified using Tonelli's theorem, which tells you can do the integration in any order of your choice. Very important result, okay? But also it raises the question that the PDF of the sum of two random variables is difficult, right? So you need to do what? You need to take the joint, and then f of xy, and then you need to replace y by z minus x, and then do an integration. So if you have three random variables, if you have the sum of three random variables, then you need like to get the PDF of the sum of the first two, and then this will be like a new random variable, and then you get the sum of this new random variable and the third one. So summing random variables is not nice. Okay. Things are a bit easier if we have independence, but still you will need to do an integration. So if x and y are independent, then basically the joint distribution can be written as the product, and basically in the integration you can write the joint as the product. So rather than having f of x comma y, x and z minus x, it is f of x and then f of y with z minus x, or you can write it this way. So if there is independence, the joint distribution can be written as a product of the marginals, and this may make the integration a bit easier, but you still have to do an integration. And if you look at basically this integration, if you are familiar with the operation of convolution, basically what we have is convolution. Basically, if x and y are independent, BDF of z equal x plus y is indeed the convolution of fx of x and fy. You don't need actually to understand convolution, because like to you it's just a formula. You can apply the formula, okay? But it's nice, I mean, for those of you who know convolution, it's nice actually to know that this is convolution. What we have here is a convolution, and we have convolution only when the two random variables are independent. Okay, so if we want to apply this result here, x and y are IID, so they are independent and identically distributed, uniform 0, 1, and so basically the PDF of each one of them, because we multiply and add, because basically, yes, this is what you do here. So you take one of the guys parameterized by x, the other one z minus x, where z is your output variable, you multiply and then you integrate. And so yes, this is how, you know, the convolution of two functions is defined. Okay, but for us, I mean, you can just implement the convolution like what I'm doing here. So basically, the PDF of x and y uniform from 0 1, and so the PDF is just the indicator from 0 to 1. And so what is fz of z? It is integral minus infinity to infinity. Now we put PDF of x. What is the PDF of x? Indicator 0 x1. Because x here given in the problem, it is uniform 0 1. Then PDF of y with argument z minus x. Okay, and so here you have indicator, and then you have 0, and now y, rather than y, you have z minus x, 1. And then you integrate dx. Okay, so you just apply the formula. Okay, so even if you don't know that this is convolution. Now, if you know it's convolution, you know, anyone knowing convolution will know that basically the result will be a triangular function, because we are basically convolving two rectangular pulses. But again, if what I'm saying is not like familiar to you, basically you can ignore it. You can just do the integration. So basically, the first indicator tells you that x is between 0 and 1. The second indicator tells you that we have this inequality should be satisfied, that 0 is less than z minus x is less than 1. Okay, and so let's see. So what is our integration now? So this first guy again tells you that x is from 0 to 1. This second inequality here can be written as two inequalities, right? So z minus x is greater than 0 means that x is less than z. X should also be less than z. Now z minus x less than 1, it means that x, if you move x to the other side, is greater than 1 minus z. So we have x less than z and x should be less than 1. From the first indicator, x is less than 1. And we have x greater than, I think, so I move x to this side, z minus 1. So this is z minus 1. And also we have x greater than 0 from the first indicator. Right, so the first indicator tells you that x is greater than 0, is less than 1. Second indicator tells that it's less than z and greater than z minus 1. And so you can combine this and do the integration. So basically you are integrating 1 when the two indicators... Yeah, I mean your function, generally what you have inside is x and y and small z. Yes, this is the general case. It just happens to us now that the integrand is 1 when the two indicators are 1, and we just need to write properly the basically the limits